Hello, we are in Chapter 1, Section 3. Today we're going to be talking about the complex numbers, and also on the second part of this section we're also going to be solving quadratic equations in the complex number system. But before we can do that, we got to understand what the idea of what a complex number is. So what is an imaginary unit? Imaginary unit, which we denote as I, is the number that the square is -1. That is, if you square the I, it equals -1. Now you can also think of that as I equals the square root of -1 if you take the square root of the other side. Now, complex numbers and imaginary numbers, let's get that straight right off the top, okay? They are not the same thing, okay? Actually, one's a subset of the other. Okay, let's understand what a complex number is. Complex numbers are numbers of the form a plus bi, where a and b are real numbers. The real number a is called the real part of the number a plus bi, and the real number b is called the imaginary part of a plus bi. And I is the imaginary unit. So I squared is -1. So put that in a little bit more clear language. A complex number is made up of two types of numbers, a real number and an imaginary number. The bi is the imaginary part. The a is the real part. So you can't combine them. You can't combine an a and a bi because they're not like terms. So a on its own is a real number. A bi on its own is an imaginary number. But when you combine them into one number, and by trying to combine them, like adding them, then it becomes a complex number. So let's take, for example, if you have 2 plus 3i. 2 is the real number. 3i is an imaginary number. But put together, 2 plus 3i is a complex number. That's the distinguishing. Like I said, a lot of people believe imaginary numbers, complex numbers, the same thing. It's actually the imaginary numbers is a subset of the complex numbers. So that's how it works. Okay? So let's begin by manipulating these. Let's learn how to add, subtract, multiply, and divide complex numbers. So properties of complex numbers. Okay, equality of complex numbers. If a plus bi equals c plus di, that's only true if and only if a equals c and b equals d. So in other words, if you have two complex numbers that are equal, then the real parts have to be equal and the imaginary parts have to be equal. So in other words, if you have 2 plus 3i, the only complex number that's going to be equal to is 2 plus 3i. So that's the property of equality. Sum of complex numbers. If you add up two separate complex numbers, a plus bi and c plus di, you would add up their real parts. So you had a plus c, and you add up the imaginary parts, bdi plus cdi. And when you do that, it becomes b plus d times I. So you just basically factor the I out and combine the coefficients of those two numbers. The difference is very similar, except you're subtracting them. And the product is a little bit more complicated. If you multiply a plus bi times c plus di, it's not like multiplying the real parts and the imaginary parts. It's more in the line of what you're used to doing with binary number expressions. You do something called FOIL. That's very similar to what you're going to be doing here. You'll multiply a times c and then bdi times di. So bdi times di, and that becomes bdi squared. When I bdi squared, I squared is -1, becomes a minus bd. So that's where the second negative bd comes from. So ac minus bd. And then, of course, a times di and c times bi is the last part. So it's like a FOIL technique, which is probably a little bit more complicated than just adding or subtracting complex numbers. But you just have to remember when you're multiplying them, you FOIL them out. So let's look at some examples here. When you add these complex numbers, 3 plus 5i plus -2 plus 3i, it's just kind of like combining the 3 plus a -2, which is 1. And then you add 5i plus 3i. 5 igloos plus 3 igloos is 8 igloos. So it'll be 8i. So 1 plus 8i. Subtracting them, very similar. 6 plus 4i minus 3 plus 6i. 6 take away 3, which is 3. And then 4i take away 6i is a negative 2i. So again, this is like combining like terms. Now let's look at multiplying. Now look at an example of multiplying them out. 5 plus 3i times 2 plus 7i. Now they do this a little different. They're going to multiply the 5 times the complex number 2 plus 7i, and then they turn around and multiply the 3i times the complex number. So it's like a distribution 2 times. It's also just another way to FOIL. And we'll show an example in a second when they actually do the FOILing technique. So you do that, you'll get 10 plus 35i plus 6i plus 21i squared. And that's where people get confused. A lot of times they'll combine the 35i plus the 6i to get the 41i, which is the next step. But they don't know what to do with the 21i squared. And they'll just leave it like that. They'll say 10 plus 41i plus 21i squared because they think 21i squared is a number that's not simplified. That's already simplified. And it does need to be simplified because, as you recall, by the definition, I squared is negative 1. And so it becomes negative 21 plus the 10, which is a negative 11, and then your 41i just drops down. Now remember, okay, when you're multiplying 2 complex number, okay, you cannot end up with 3 terms. You might end up with 1. Most of the time you'll end up with 2 terms. There is a time that you'll end up with 1 term. We'll talk about that in a bit. But that's when you're multiplying 2 special types of numbers. But when you're multiplying 2 complex numbers, typically you'll get a complex number. And a complex number is written in the form of a plus bi. Like I said, there is an exception to that. There are 2 complex numbers that you can multiply, but they are related to each other. And we'll talk about that in a bit. Alrighty? So definition. Okay, if z is equal to a plus bi, now they're letting z just be denoted by a plus bi, and it's a complex number, then the conjugate is denoted by z bar, with a little bar above the z, and it's defined as a minus bi. A lot of people get these confused with opposites. The conjugate is only the opposite of the second term. If you take the opposite of a complex number, a plus bi, you would get negative a minus bi. So both terms are opposite of it. So for example, if you have 5 plus 3i, the opposite is negative 5 minus 3i. Whereas the conjugate is only 5 minus 3i. It's only the opposite of the second term, the imaginary part. Okay, so taking the opposite is taking the opposite of the real part and the imaginary part. Whereas the conjugate is only the opposite of the imaginary part. The real part stays the same. So that's the difference. It's a big difference between those two. Okay, so let's look at an example here. So multiplying a complex number by its conjugate. So find the product of a complex number z, which is 3 plus 4i, and its conjugate z bar. So we know 3 plus 4i is the complex number, so its conjugate is 3 minus 4i. Now multiplying a complex number times another complex number, but it's a special complex number, 3 minus 4i. So if you FOIL it out like we had been doing, 3 times 3 is 9. 3 times negative 4i is negative 12i. 4i times 3 is a positive 12i. And then 4i times negative 4i is a negative 16i squared. Now, of course, the i's are going to cancel this time. So it'll be negative 12i and a plus 12i cancels out, leaving me with 9 plus 16. Why is it plus 16? Now remember, negative 16i squared. I squared is negative 1. So it ends up being negative 16 times negative 1, which is a plus 16. But look at the final answer. It's 25. Where's the I? Well, the I canceled. So this is a case when you multiply a complex number times another complex number, and the result is technically a real number. Okay? So that's what happens here, okay? But that's the only case when you multiply a complex number times a complex number and the result is a real number. Most of the time, it's a complex number times a complex number is a complex number, but not in this case. Alrighty? Alright, let's look at this theorem. So here I wrote, it's just spelled out to you. The product of a complex number and its conjugate is a non-negative real number. That is, if z equals a plus bi and you multiply that by its conjugate, the result is a squared plus b squared. and it will be non-negative, meaning it cannot be negative. It could be 0, but it will be non-negative. Okay, so most of the time it will be a positive number, though. All right, so let's look at an example here. Okay, now this is when we are dividing. Now notice this is division. Now it says write each of the following in standard form. So this is dividing a complex number by a complex number. So we have 1 plus 4i divided by 5 minus, what is that, 12i? Yeah. So now you're dividing two complex numbers. Now it's very tempting to divide the 1 by the 5 and the 4i divided by the negative 12i. Now if it was that simple, we probably wouldn't even be discussing this, okay? But a lot of people don't know what to do with it. Well, this is where the conjugate comes in handy again. Because remember now, if you multiply a complex number by its conjugate, then you get a real number. So if I multiplied the bottom, because the I in the bottom is really annoying, because what if the bottom number was, let's say, 5 altogether, just 5? Then you'd have, well, 1 plus 4i divided by 5 is going to be 1/5 plus 4/5 I, right? Because you're just dividing both the parts on top by 5. If you're dividing just by 5. So it'd be 1/5 plus 4/5 I. That's if it was a real number. But it's not a real number. It's 1 minus 12i. It's a complex number. So we need to make the bottom number a real number. How do we multiply a complex number to get a real number? Yeah, it's the conjugate, like we talked about before. So we take the 1 plus 4i divided by 5 minus 12i, and we multiply the top and the bottom by 5 plus 12i, the conjugate. And you're like, why don't we just multiply the bottom? Well, you can't just multiply the bottom by the conjugate because it would change the problem. By multiplying the top by 5 plus 12i, you're actually multiplying by 1. And as we know, multiplying by 1 on anything doesn't change the problem. So that's why the top and the bottom has to be multiplied by the conjugate 5 plus 12i. So you can't just pick and choose what you want to do. Now, but look what the bottom turns out. The 5 minus 12i times the 5 plus 12i, you remember it's a squared plus b squared. So it's going to be 25 plus 144. But notice that number is 169, and that is real. And the top number, you just have to FOIL out like you do a regular product. So it'd be 5 plus 12i plus 20i plus 48i squared, and you just have to simplify that down to a negative 43, because remember 48 times I squared is a negative 48, and then negative 48 plus 5 is negative 43. And of course 12 igloos plus 20 igloos is going to be 32 igloos, 32i. And of course remember 25 plus 144 is 169. And like we said prior to this, if we're dividing by a real number, it's just a matter of separated into two parts. So it becomes negative 43 over 169 plus 32 over 169. Yeah, the answers when you divide complex numbers by complex numbers, usually you end up with fractional coefficients. The real part and the imaginary part would become fractions. That can't be helped, but they are complex numbers. Alrighty, and this is probably the most complicated operation of complex numbers is division. And the reason that is because you're introducing something in the problem that wasn't there to begin with, namely the 5 plus 12i divided by the 5 plus 12i. All right? So let's look at the next one. Let's see if we can get another example off of this. So we have 2 minus 3i over 4 minus 3i. What does that equal to? Well, we got to multiply it by the conjugate, which is 4 plus 3i over 4 plus 3i. Then remember the bottom is a squared plus b squared, so it's going to be 16 plus 9, 4 squared, 3 squared. And then the top, you just FOIL it out. So the bottom becomes 25, 16 plus 9. And then remember the negative 9i squared is positive 9, plus the 8 is 17. And then 6 igloos, take away 12 igloos is negative 6 igloos, or negative 6i. And then you get to separate it into two parts because we want to put it in standard form. So, why do we always put it in standard form? Why don't we just leave it like 17 minus 6i over 25? I get that question quite a bit. Because it's not standard form, okay? And the reason is, what do you mean by standard form? Well, the real part and the imaginary part has to be separated. So they cannot be connected. And if you put it over 25, they're connected. So you have to be able to distinguish between what is the A and what's the B. So what's the A here? 17 over 25. What's the B? Negative 6 over 25. So you like, is the step right before it correctly? Is it correct really? Yeah, it's correct, but it's not written correctly. And we have to write it in the correct form. All right? So let's look at the next theorem here. Okay? So the conjugate of a real number, is the real number itself. Okay? So for example, if you have the number 9, the conjugate of 9 is still 9. And you're like, wait a minute, I thought that was negative 9. No, that would be the opposite of 9. Now you're like, well, what do you mean with the conjugate of a real number? Well, there is no bi. So when I said 9, it's really 9 plus 0i, if you want to get technical. So the conjugate of that would be 9 minus 0i, which is still 9. Whether you add 0i or you subtract 0i, it's still 0i and becomes 9 nonetheless. So that's a really trivial theorem, but it is true. Next one is, it says the conjugate of a complex number is the complex number itself, which kind of makes sense. So if you take z bar of z bar, if you take z bar bar, which is still z, and it makes sense. Because like I said, if you take 3 plus 4i, that's the complex number I'm going to begin with. Take the conjugate, it's 3 minus 4i. Take the conjugate again, back to 3 plus 4i. So that makes sense. The next two are just a couple of things that fall through. We're not going to be dealing with this much in this course, but I wrote it down just for you guys to see it anyway. But if you take the conjugate of two complex numbers after you added them up, that would be the same answer as if you took the conjugate prior to that and then add them up. So whether you add first and then take the conjugate, or take the conjugate of the complex numbers first and then add, the result will be the same. And that last one is the same is also true if you multiply them. So taking the conjugate of two complex numbers, so multiply the two complex numbers first, take the conjugate, okay, or take the conjugates at the beginning, then multiply those conjugates together, the end result will be the same. So that's what that is saying. All right, so powers of I. Okay, this one's fun to work with. I is to the first, of course, is I. I to the second, by definition, we know it's negative 1. So these are the ones we spring off of. Now, what is I cubed? Well, I cubed is I squared times I. Now, I squared we know is negative 1. So negative 1 times I is negative I. So yes, I cubed is negative I. Now, what about I to the fourth? Well, I to the fourth is I squared times I squared. And both of those are negative 1, so the final result is 1. Now let's go to the next column. Look at I to the fifth. I to the fifth turns out to be I to the fourth times I to the first, which is I. Because remember, I to the fourth was 1. So I to the fifth is the same thing as I to the first. Now look at I to the sixth. I to the sixth is I to the fourth times I to the second. And I to the fourth, again, is 1. I to the second is negative 1. And when you multiply them out, that's negative 1, which that is the same thing as I squared. So as you can see, the first column is lined up with the second column. I to the third is the same thing as I to the seventh. I to the fourth is the same thing as I to the eighth. So what we call it is it's cyclic. What that basically means, it cycles over and over again. So in other words, if you had I to the 15th, that would be the same thing as I to the 11th. And I to the 11th would be the same thing as I to the 7th. And I to the 7th is the same thing as I to the 3rd. And of course, I to the 3rd, of course, is negative I. So they just cycle over again. All right, so let's look at an example of this. Let's look at I to the 27th. Now, I to the 27th is the same thing as I to the 24th times I to the 3rd, of course. 24 plus 3 is 27. Now you're like, well, why did they choose 24? Well, 24 is a multiple of 4. So we know I to the 4th is 1. So I to the 24th is I to the 4th times I to the 6th power. And we know that's to be 1 to the 6th. So it turns out to be I cubed, which is negative I. So I to the 27th is the same as negative I. So like I said, it just cycles over. So get another one. Ooh, I to the 101th power. Looks very daunting, doesn't it? It says 101. Well, 101, let's go prior to that. 100 is a multiple of 4. So I to the 101st is I to the 100th times I to the 1st. And of course, I to the 100th is a multiple of 4, so we'll have the same answer as 1. So it'll be 1 times I, which is I. All right? So those are evaluating powers of I. This is not a major part of this course. It's something that might end up being on the final exam as a problem or so, but it's not going to make or break you. It's not a main emphasis of the class. This is what I just basically call a little extra tidbit of the course. Kind of interesting, but it's not a major player of the course. So it's worth knowing, though, and you might end up seeing this again at some other point in time. All right. So that concludes this video. If you have any questions on this one, you let me know. It's for some of you guys, it begins a new era because you thinking real numbers is all you had. Well, we've actually added another layer, which we call the complex numbers. And a lot of you guys already have heard of the complex numbers already to begin with. So hopefully we're all up to speed at this point. All righty. So if you have any questions, like I said, give me an email, and you have a good day.